Thank you, Chairman. And I would like to thank all of you for joining us. And I'm Masato KOASHI from University of Tokyo. And I'm very happy to have an opportunity to report the progress of our project called Research and Development of Theory and Software for Fault-tolerant Quantum Computers. So these are the outline of this talk. And I'd like to start with the overview of the theory software project. So for the next 3 days, we will be hearing about various projects in the Moonshot Goal 6, which includes various physical systems and networks and integrated systems. Now, the theory and software project is a kind of cross-divisional project where the theoretical researchers are gathering into a single project. So, our project is about how we can contribute to the realization of a fault-tolerant quantum computer. And the goal of the Moonshot Goal 6 as a whole is a realization of the FTQC by 2050. So until that time, the performance of actual devices will steadily increase thanks to the effort of experimental researchers. And at the same time, the theoretical researchers can contribute by exploring many possibilities and lower the bar, relax the required performance of the actual devices. So the goal of our project is to make this curve, meet this curve by 2050. Now, what can we do toward this goal? So at this point, I would like to introduce project PIs. So currently, there are 14 groups, and these are very strong theoreticians from institutes all over Japan and have expertise on various subjects. So with these PIs, I'm pretty much sure that the steady research and breakthrough ideas will lower the bar here significantly at the scheduled end of the Moonshot program. But we now have a very unique opportunity to gather a wide variety of researchers. So I would something more, something that helps to accelerate trends of this curve. So to do that, we need some stratagems, and in our project, we chose to develop a cross-layer co-design models. And fault-tolerant universal quantum computer is a very complicated system with many layers, just we have learned from the previous tutorial talk by Fujii-san. And cross-layer co-design model is a set of connected software stacks that includes all the metrics and trade-off relations in these layers. And through optimization and simulations, predict the performance of the FTQC. And now I believe that the construction of this cross-layer model will benefit the project in a variety of ways. So in the development stage of the cross-layer co-design model, it works as a hub to promote research in the project. And once the prototype of the model is constructed, and then it will work as a pilot to guide the researcher, theoretical and experimental included, in the Moonshot program toward its goal. And finally, eventually, the model can put together the state-of-art results in each layer to produce the optimized design of FTQC, serving as a kind of dynamical blueprint. So I'm sure that the construction of cross-layer co-design models will contribute to make an accelerated trend here. Okay, so let me give you what we have done in these 2.5 years. And let me begin with the cross-layer co-design model and the related results first. Okay, and so let me give you a little bit more detail about cross-layer model. So what we expect from the model is it's going to tell us the trade-off relations across multiple layers. And it also tells us the true impact of some technological improvement in some layer. And also, it demonstrates the current state about design by unifying proposed technologies. And to do that, we plan to implement various functions, such as evaluating the performance for a given FTQC configuration, and then optimizing parameters of FTQC to maximize the performance. And also, we build lightweight mock-up modules, which are to be substituted depending on the available computational resources. Now, what we have accomplished so far is to build a prototype of this cross-layer model, which is capable of this. So that is software stacks for all the layers connected to each other, so that it can evaluate the performance of the whole computer. And we did that for a specific FTQC architecture, which assumed superconducting qubits and 2D surface code, which I believe is a mainstream one. And using this prototype, we built a model of quantum computer solving a specific problem, that is estimation of the ground state energy of some interacting many-body system. And the model gives us various specific numbers, such as the number of physical qubits or computational time, or it even gave us power consumption. And this is not just a demonstration, but obtained numbers are also important, because the number here, the 500,000 physical qubits, this is the smaller than the known required size of quantum computer that solves a meaningful problem faster than a classical computer. So it's kind of amazing that this model pays an unprecedented level of attention to the details, but still obtain these numbers. Okay, so next I would like to introduce a couple of results that are obtained in close relation to this cross-layer model. And the first one is a kind of close-layer attempt to solve an issue. The issue in this case is inhomogeneity of the superconducting qubits. And it is reported that in a single chip, the lifetime of the superconducting qubits varies. So if we use these qubits to form a code, then without any countermeasure, the quality of the logical qubit will be very bad. Now, our solution is to remedy this in the layer of error correction by providing a circuit design for a decoder for the surface code. And main idea is to construct a partial lookup table based on the information on the locations of the bad qubits. And here, the balance between space and time is the key. So if the decoder try to arithmetically compute everything to find the best guess on the error patterns, considering the position of bad qubits, then it would take too much time. And contrary, if we put every possibility into a lookup table, then the decoding would be fast, but it would not scale well. So this proposal kind of tried to hit the good balance between them. And it demonstrates the effectiveness by using a very detailed model connecting the error correction layer and the very bottom of the hardware layer. And this is another example of a software solution to a hardware problem. And recently it was reported that cosmic ray events is non-negligible for a quantum computer. So even for this small size of chip, once in 10 seconds, cosmic ray event occurs, and it raises the error rate by a factor of 30 in the vicinity for a certain period of time. Now, this kind of time-varying properties requires special attention, because if we use a big code sufficient for the worst-case error, then the overhead is too much. Now, the entity group has provided a very elegant solution that is very feasible in the current architecture for surface code. So this is kind of a search and destroy strategy. So to know when and where the cosmic ray hits, then eliminate the threat by temporarily enlarging the code. Now the interesting feature is that in the FTQC architecture, the syndrome is repeatedly measured all the time. So the clue about cosmic ray event is already there. And also, enlarging the code in the real time might sound like a big thing, but daunting thing. But actually, in the user framework, actually the logical operation on the logical qubits is actually done by something very similar to changing the codes. So this is also a kind of mundane procedures. So they can design a very feasible style for this kind of strategies. Now, applying this strategy, the hardware requirement improves from this curve to this curve, almost the same level of the requirement when there is no cosmic ray events. Okay, so then I would like to proceed to various interesting results from participants of the project. The first, I will talk about several results regarding quantum error correcting codes and fault tolerance. And the first one is close to a mainstream one. So I'm talking about surface code again. And this is about connectivity. So on surface code, the qubits are arranged in square lattice. So each qubit is connected to 4 qubits. And we must select which qubits to interact. But that selection experimentally is not so simple and causes an error via crosstalk. So sometimes the number 4, even 4 is too many. So it will be better off if it is 3. So that's why, for example, the IBM proposed a method using a different code, honeycomb code, which connection is 3. Now, Osaka University tries to maintain the advantage of surface code and reduce the connectivity to 3 at the same time. And that was done by using this structure. So for each of the qubits in surface code, it is replaced by a tiny code of just qubits. Then the connectivity becomes 3. Now, this tiny code also, tiny code itself is also helpful. Of course, this is too weak to do any error correction, but this can do the error detection. So it can raise a flag if something is wrong. So they constructed a new decoder that can utilize the information of flags. Then this is a graph of logical error probability versus physical error probability. And this clearly shows that with flag information used in the decoding, the performance of the code improves much. And the derived threshold values is not so bad compared to the original surface code. And this is surely better than other code of connectivity of 3. And so far, I talked about surface codes only, but there are many other codes which are to be explored fully, which are not yet explored fully. So, for example, the color codes. Color codes has a unique advantage of all the Clifford gates can be implemented easily by applying transversal application of gates. Of course, the color code also has disadvantages. So we want to know the true usefulness of the color code. But one obstacle here is the difficulty in decoding. So this makes then even a performance evaluation to be not so easy. So Osaka Group proposed a new decoder based on the reduction to a well-known numerical optimization algorithm. So if we replace each of the stabilizer operator by a classical spin, then finding an error pattern with a minimum error weight can be shown to be equivalent to a higher order Ising problem. So we can use simulated annealing to decode the color code. So compared to the known algorithm of exact optimization called Cplex, simulated annealing is, as you see, it's much faster. But derived performance curve almost coincides. So it is good. So with this new tool, we expect to figure out the true potential of the color code, and also the mechanism of this new decoder is quite general, so it's applicable to various other codes. Now, as for the decoder, there is an interesting finding from OIST group. And there was a common assumption, commonly believed that the useful quantum decoder should be able to correct all the constant weight errors. That means it must correct all small weight errors. If this is true, then, for example, the simple decoder called flip wouldn't work. So in a flip decoder, the error pattern search is locally done by flipping just one bit at a time. So it's very fast, but it's easily caught up in the local minima. So it fails to correct even the very small weight of errors. Now, OIST found that a decoder based on this flip decoder actually works for the 3D toric code. So compared to the best known, actually threshold value is not so bad, and runtime scaling is much, much better. So I think this findings opens up a new possibility for the fast decoders. Okay, we are also tackling more fundamental questions. So question here is a question of ultimate cost of FTQC. Okay, let me define the overheads of the fault-tolerant computing first. So as we try to solve the problem of size m, we want to run a quantum circuit of W qubits and D steps. But to fight against the noises, what we're going to do is to simulate this circuit on the FTQC circuit, which is, of course, bigger than this. Now, the ratio of the number of qubits to the original is called space overhead, and the ratio of steps is called time overhead. Now, so we want to know the scaling of these overheads over the size of the problem. Now, if we look back to the history of the fault-tolerant quantum computing, then originally we tried to do the fault-tolerant by concatenated codes. So by nesting the same small code, like 7-qubit code again and again, then we can solve any size of the problem. But of course, the number of qubits grows rapidly from 7 to 49 to 300 something. So the space overhead is not so good. Now, nowadays, people's interest has been shifted to a big code rather than concatenated codes. And to solve a bigger problem, just use a bigger code with a larger distance and with more logical qubits. Now, interesting thing is that there is a family of good code which achieves constant space overhead in this case. But this also has a disadvantage that the gate operation cannot be operated in parallel. So the time overhead is not so good. Now, our approach here is a kind of revival of the concatenated codes. But the novelty here is that instead of repeating the same code again and again, we use a series of gradually growing sizes of codes, like quantum Hamming codes. So we kept the code distance to 3, but the number of logical qubits increases and the rate approaches unity. Then we can show that this architecture also achieved the constant space overhead. Now, for this architecture, we can apply the quantum gates in parallel. So the time overhead is much better than before. So I think this new finding will shed a new light on the design of the FTQC in general. Okay, then let me get back to a more down-to-earth topics, and let me tell you about some hardware-specific results. And these are the efforts for developing simulation or optimization tools, which is essential for the theoretical study of specific physical systems. Now, the Riken group has been developing an open source numerical package called QTIP, which provides general simulation of open quantum systems. And recently, it achieves more than 1 million downloads. And for the development of quantum computer, they recently released a new package that addresses pulse level simulation of noisy quantum circuits. And this year is about optical systems. So nowadays, thanks to the improvement of the photon counters, now it looks like it's possible to synthesize non-Gaussian states for over the multiple modes. But the computational cost for designing this synthesizing circuit cost grows rapidly as the number of modes increases. So this proposal provides a new clever way of searching to reduce the computational cost to polynomial instead of exponential. And this here is similar in that it reduced the cost of it reduced the computational cost, but the target here is the superconducting qubit and interacting with the microwave cavity. And in the regime of the large amplitude, where the perturbation is not allowed. But here, using the novel method of using displacement operator, it succeeds in reducing the computational costs. Now, let me give you a very interesting discovery in the field of circuit QAD or AMO. So if you place a bunch of atoms, or qubits of atoms, and drive them by a coherent laser, then a dipole moment oscillates in sync, as if there are a big dipole moment. So various enhanced effects is expected. But this is not so surprising. But if there is no coherent drive, then it is not so trivial whether such kind of cooperative effects occurs or not. And the only known occasion is the famous decade superradiance. So here, the spontaneous emission from a single atom becomes n times faster if there are n atoms, because they start to spontaneously oscillate in sync. Now, the Tsukuba group have recently shown that theoretically shown that the opposite phenomenon is also feasible for a certain setup. That is, absorption is also accelerated. So combining the acceleration of radiation and absorption, we can form a heat engine. So in this case, the cycle of the engine is n times accelerated, and the power of that engine is now proportional to n squared. So the fact that the thermal process without any coherent control can benefit from the cooperative effects, I think it's very interesting. It might be open a new possibility for the fast control of the qubits. Okay, so this slide is a collection of results related to distributed architectures. So this here is an approach from the fundamental side. So it's about distribution of entanglement to remote chips using light. So when you use a dispersive interaction between matter qubit and light pulse, then actually we can derive the optimal yield of entanglement. It's a fundamental limit. And that limit is also achievable with photon number counting. And since this optimality is largely independent of how this entanglement is going to be used, so this is kind of a general. So I think it gives a good starting point for investigating various possibilities. And this here is a model case of collaboration between theoretician and experimentalist. So the idea for demonstrating swap gate between microwave photon qubit and the superconducting qubit is actually carried out experimentally, and a fidelity of around 0.8 was confirmed. And interesting feature of this method is its simplicity. So the photon is just reflected back, then the quantum state is already swapped. Okay, and here the distributed distributed architectures are often regarded as a kind of obstacle But once it is realized, then it has also an advantages. And such an example is proposed by KO group, where the burst errors is effectively protected by using a quantum error correcting code across the remote chips. Okay, so for the last part of the progress report, I would like to say a few words about NISC and FTQC. So as you know, there is a big gap in the scaling between the NISC and the FTQC. And this gap is kind of discontinuous in the sense that you have to invest a large initial overhead before you start to benefit from FTQC. And now, this project is, of course, dedicated to this FTQC, but some of the participants are also proficient in the NISC technology. So as a result, there is a couple of results that kind of bridging the gap between NISC and FTQC. And one is the idea of surpassing this bound in NISC computing by using FTQC technique. And in the previous tutorial talk, Fuji-san already talked about this new early FTQC architecture. And the other one is to use NISC technique called error mitigation to reduce the overheads in FTQC. So let me elaborate on it a little bit more. So there are many different methods for error mitigation, but here I would like to focus on so-called probabilistic error cancellation. Now, if we know the noise exactly as a mathematical map, then if we could apply the inverse map, then of course error would be canceled. But this is impossible because this inverse is not physical. But the linear combination of fortunately, this inverse map can be decomposed as a linear combination of physically feasible processes. So if your goal is to estimate some expectation value, then there is a solution. So you just run the various quantum circuits with changing these physical gates, then take a linear combination. Now, let us consider applying this method to logical qubit in the FTQC. Now, the first observation is that the errors on the logical qubits tends to be approximated by Pauli errors. So this N is Pauli, then this Bi is also Pauli. Now, usually FTQC is running on the so-called Pauli frame. So in that case, the Pauli gates here is always be absorbed by this classical processing. So the end result is that you don't need to do nothing for the quantum circuits. So just change the classical processing to achieve the error cancellation. So it's even simpler than the NISC. And if you see this graph, then to achieve the same level of accuracy, this method requires a smaller code distance. That means the smaller overhead of the qubits. Okay, so that's it for the progress reports, although there are many other results which I don't have time to mention, unfortunately. So let me summarize. Let me summarize the current progress of the project. So we have constructed connected software stacks, including all the layers of FTQC from hardware to software. This is a prototype across the co-design model. And it already contributed to several research outcomes that are impossible without the model, such as proposal of solution across multiple layers. And the participants of the project in each layer are also steadily developing various approaches toward reduction in hardware requirements for realizing a fault-tolerant quantum computer, which ranges from mainstream methods or pioneering new possibilities or deepening the fundamental understandings. So I would like to continue our plan to improve the software stacks such that they enable co-designing now and make them really useful tool. And at the same time, we will continue various attempts in each technology layer for reducing hardware requirements. And eventually, we expect kind of cycles of harvesting and cultivating of this co-design model in which researchers exploit the model to accelerate their research and feedback outcome back to the model itself to help the evolution of the model. Okay, that's it. And I would like to, I would like to thank all the project peers again. And I'm sorry not mentioning by name, but I would like to thank all the participants in the project. So thank you for listening.